So the rest of this video now is going to be devoted to trying to find the PDF of the chi-square distribution with n degrees of freedom. And what we're going to find out is that actually the chi-square distributions, they are special cases of the gamma distribution. So chi-square distributed with n degrees of freedom is actually the same distribution. We'll find that its PDF is the same as the gamma distribution with alpha parameter n over 2 and beta parameter a half. So this chi-squared random variable v distributed chi-squared with n degrees of freedom is actually gamma distributed n over 2 a half. So understanding this is going to be the focus of the remainder of the video. So let's think then about what the PDF of this random variable v, which is chi-squared distributed with n degrees of freedom, is going to be. So to tackle this problem, we're actually going to start with a simpler problem, which is we'll take the simplest chi-squared distribution, which is the chi-squared distribution with 1 degree of freedom. So we'll call the random variable u, and it's going to be chi-squared distributed with 1 degree of freedom, and it's going to be defined as x1 squared, where x1 is distributed normal 0, 1. And let's try and work out what the PDF of this is going to be, and from that we'll then expand and work out what the PDF of the general chi-square distribution with n degrees of freedom is going to be. So to work out the PDF of this, we're actually going to work with the CDF initially. Whenever you're working or doing transformations of random variables, it's always better to work with the CDF. You are very liable to get it wrong if you work with the PDF. So we'll work with the CDF, and then we'll differentiate it to find back again what the PDF is going to be. So let's consider the CDF for this random variable u. So the probability that big U is less than or equal to little u. Let's think about what that's going to be. Now firstly, let's just think about what the range space of this is going to be. x1, the random variable x1, can take on any number from negative infinity to infinity, however you then square it. So you're never going to get a negative number here. So u is never going to be a negative number. Now 0 is a little bit problematic. Intuitively, x1 could equal 0. I've drawn actually that this is supposed to be the standard normal here, so you can see that actually 0 has the highest probability density of any number for the standard normal distribution. So x1 could be 0, however the actual probability, remember this is a probability density, not a probability mass function, so the actual probability that you'll get any specific number, even 0, which has the highest probability density, is 0. So 0 is going to be a difficult, a problematic number with regards to the PDF of this. You'll see when we find the PDF of this that it has an asymptote at 0, so it's not actually going to be defined at 0. You're going to end up having to divide through by 0 if you were trying to apply this PDF to 0. So 0 is a tad problematic. However, the PDF is going to work then for all the other positive numbers. So we'll ignore 0, we'll fudge it a little bit, just don't worry about that, because actually one single number doesn't make any difference to the entire probability distribution, not when you've got an uncountably infinite other numbers that it could be. So don't worry too much about 0. The probability density function that we're going to derive isn't going to work at 0. There's going to be an asymptote at 0, but it doesn't matter that it doesn't work at 0. It's going to work for all the other positive real numbers. So this PDF that we're going to find, it's going to be valid for u is greater than 0. We're not worried about the negative numbers. We understand that it can never equal them, and we're going to turn a blind eye to the issue that happens at 0, because it doesn't actually matter what happens at one single point. What's important is what's happening at the continuum, uncountably infinite number of points. So let's try and work out then, what is the probability that big U is going to be less than or equal to little u, where little u is some positive real number then? Well, remember x1 is being drawn from the standard normal distribution, so then we just have to think about what values in the range space of the standard normal distribution are going to be mapped onto the right portion of this, i.e. they're going to be mapped onto something less than u. Well, if we take the square root of u, which is what I've got here, we've got minus the square root of u and the square root of u. If you consider what that's going to be mapped onto, when we square it, it will go to u. When we square this one, it will also go to u. So these will be bang on this point. And then if you consider all of these numbers in between negative the square root of u and the square root of u, so if we took this number here and squared it, it would be mapped onto something that is smaller than this, so it would be in the correct range for this. So actually, if we want to know the probability that when we do this square, we'll get something less than u, we need to know the probability of being in this range, i.e. we need this area here under this PDF. So this phi is the notation for the CDF of the standard normal. So if we take phi at the square root of u, that gives us all of the area up to this point. So all the way from negative infinity up to here, all of that function integrated, that's that value. If we take phi of negative the square root of u, that gives us the area under the curve all the way up to minus the square root of u, so it gives us this tail area here. So if we take this one and take this one away, then we'll end up with the bit that's in the middle, which is the bit that we want. So we've taken all of this area here, and then we've subtracted off this tail here, so we'll be left with just the area there. So that's going to be the probability that u is less than or equal to little u. So now what I'm going to do is differentiate this to get the PDF for my random variable u. So this PDF is going to be valid for u greater than 0, and you'll see why this process actually goes wrong at u is equal to 0 when we perform this differentiation. So if we differentiate this now with respect to u, so this is just a bit of the chain rule. So differentiating this capital phi will give us lowercase phi. So the CDF of the standard normal is going to go to the PDF of the standard normal, which is denoted by lowercase phi. So lowercase phi evaluated at the square root of u, and then we need to times it by the derivative of the square root of u, and that's the problem. The derivative of the function, the square root of u, is infinite at 0. All the other positive real numbers, it's fine, it's not infinite there, but at 0 it becomes infinite. So that's where it breaks, this process, if we try and do it for u is equal to 0. So we'll turn a blind eye to that. We'll just say u is greater than 0, because that one single point doesn't actually matter as far as the whole probability distribution is concerned, because the probability of being any one single point is 0 anyway, or infinitesimally small anyway. So, differentiating this then, this is u to the power of a half, so bring the half down and then lower the half by 1, so we'll get a half u to the negative a half, which is 1 over 2 the square root of u. So that's this bit differentiated. Then let's differentiate this, so we'd still have a minus here. We differentiate this, it gives us lowercase phi, evaluated at minus the square root of u. Then we differentiate this, so it's minus u to the half. Again, the half comes down, so we'll get minus a half u, and then lower the power by 1, so we'll get minus a half. So we're multiplying this through then by minus 1 over 2 the square root of u. That minus then cancels with the minus here, which is why I've written plus here. So we'll get plus phi at minus the square root of u over 2 the square root of u. Now this is wonderful because actually the PDF of the standard normal is symmetric, so the value at the square root of u is the same as the value at minus the square root of u, so we can just replace this with phi at the square root of u, and then we can combine these two together and you'll see that the over 2 here cancels. So this is just the same thing as phi at the square root of u divided by the square root of u. So now, and remember this is valid for u, it's greater than 0. And you can see that there is a very big problem if we put in u is equal to 0. So now all we need to do is remember the formula for the standard normal PDF, put it in place of phi here, and then put in the square root of u. So remember the standard normal PDF is 1 over the square root of 2 pi e to the negative, and then it's usually a half x squared, but we need to put in for x the square root of u, so we'll have the square root of u squared, which will just come out as u. So writing that out, we've got 1 over the square root of 2 pi, which came from the PDF of the standard normal, then we've got over the square root of u, which came from here, and then we've got e to the negative a half of the square root of u squared, which is obviously just u. So here then is the PDF for our chi-squared 1 distribution on the positive real numbers. And you can see again, there's an asymptote at u is equal to 0. But that's okay, we'll turn a blind eye to that, because actually if you perform the improper integral of this from 0 to infinity, it will still come out as 1. So this is still a valid PDF. Now, observe, I claim that this PDF that we have just found on the positive real numbers, and remember it's 0 on the negative real numbers, and there's an asymptote at 0, I claim that that is actually a gamma distribution. So I've written down here a reminder of the PDF for a gamma distribution. So if you have a gamma distribution with parameters alpha and beta, this is the PDF on the positive real line, and then it's 0 on the negatives. So it is beta to the power of alpha over gamma of alpha x to the power of alpha minus 1 e to the negative beta x, for x is greater than 0. Now, I claim that if I put alpha is equal to a half and beta is equal to a half, it gives me this thing. So let's have a look at this. So let's start with beta. If we put in beta here, we'll get e to the negative a half x. So yes, okay, we're using u here rather than x, but that's matching up. Then here, if I put in alpha is equal to a half, we get x to the half minus 1, which is minus a half, so x to the power of minus a half, which is 1 over the square root of x. So we've got 1 over the square root of u here, so that's matching up as well. We'll ignore this bit for a moment. Then we've got beta to the power of alpha, so put in this, a half to the power of a half, so that's 1 over the square root of 2. We've got a 1 over the square root of 2 here. Yes, we've also got a 1 over the square root of pi, but let's split this up into 1 over the square root of 2, 1 over the square root of pi. So we've got the 1 over square root of 2 being handled here. So all that I need to make sure of to settle this once and for all is that gamma of a half is equal to the square root of pi, and then these two will match up completely. So let's remember the definition of the gamma function. So gamma of a half is going to be the integral from 0 to infinity of x to the power of whatever you've got in here, minus 1. So a half minus 1, which is minus a half, times e to the negative x dx. So that is the definition of the gamma of a half. Just rewriting that, that's the integral from 0 to infinity of 1 over the square root of x e to the negative x dx. So how are we going to evaluate this integral and find that it's equal to the square root of pi? Well, we're going to perform a substitution. So the substitution we're going to make is going to be x is equal to u squared, and this is a very nice substitution because on the positive, or in fact the non-negative real numbers, this is going to be a bijective map. So I've drawn the picture here. So if we let this represent u and this represent x, then if we look from 0 to infinity, this is being mapped onto 0 to infinity in a bijective way. So it's surjective, it's onto, it's mapping onto this interval from 0 to infinity, and it's 1 to 1, so each point here has one point here that's being mapped onto it. So it's a nice invertible map, perfect for doing substitution with. So if we make this substitution, the limits are going to remain the same because we're integrating from 0 to infinity. You can see that we still need to integrate from 0 to infinity if we're integrating over u. So it's going to be the integral from 0 to infinity, and then we'll have 1 over the square root of u squared, and that's why we've done this substitution, because now the u squared will cancel with the square root to just give us u. And then we've got e to the negative u squared now, because we've substituted in for x, u squared, and then we need to replace dx with what it is in terms of du, so just differentiate this, you'll get dx by du is equal to 2u, therefore dx is equal to 2u du, so we'll put that in here. So if we now do some cancellation, we've got 1 over u here, which will cancel with the u that we've got up here, so we'll then just end up with the integral from 0 to infinity of 2 times e to the negative u squared du. Now, this is a famous integral. This function e to the negative u squared, or e to the negative x squared if we used more classical variable names, is a really famous function. It's the Gaussian function, and it's symmetric in u. So actually 2 times the integral from 0 to infinity of e to the negative u squared is the same as just doing this integral not from 0 to infinity but from negative infinity to infinity. Because if you integrate this function from negative infinity to 0, it's the same as if you integrate it from 0 to infinity because it's symmetric in u. If you put in negative u here, you get the same as if you put in positive u. So 2 times this is just the same as the integral from negative infinity to infinity e to the negative u squared du. And as I say, this is a really famous integral. This is the Gaussian integral. You may well know the answer to this, that it is the square root of pi. I will just remind you of the argument as to why it's the square root of pi, because it's a brilliant, really important part of probability theory. But hopefully you recognise that integral is the Gaussian integral and know what the answer of it is.